Okay, great. Thanks everyone for coming back to our third lecture of quantum recursive programming. So today, I think we will finish the first two parts. Recall that last time we have defined some syntax and semantics for the two quantum programming languages that has quantum control flows. So today we will finish this definition of the quantum recursive programming languages and then go through several examples. Okay, so recall what is quantum recursion. So quantum recursion is first feature we have quantum control flows. And the second feature, recursive procedural call. So the quantum control flow in our language is guarded by the QIF statement. So let me just briefly recall what this intuitively means. So a QIF statement is a quantum version of the classical if then else statement. So for classical if then else, you have this control flow and you are checking a Boolean expression B. And if B is true, then you go to the first branch. If B is false, you go to the second branch, C0 and C1. But for quantum control flows, we can go into two quantum branches in superposition. That means this quantum coin, or this quantum variable, which is a qubit variable that guards this quantum if statement, can be in the superposition state. So Q here can be in the superposition state. For example, alpha 0 plus beta 1. Then when you execute this QIF statement, you will go into this quantum branch, C0 and C1, into superposition, and they have this amplitude, alpha and beta. So that's intuitively the quantum control flows. And the recursive procedure call, this is like the classical programming. So you can define a procedure with some classical parameters. For example, if we just have one classical parameter n, then we can define this procedure. This is called the procedure identifier, and here is the procedure body. We can define it like something n. You can call the procedure p itself with different parameters. For example, you can call it, then you call it again. So this is recursive procedure call. And when you combine these two programming features, you can create the quantum recursion. So I will just draw a diagram. You will create some quantum branch here, and you can define some, you can call some programs or procedures. And each of these procedures can be, so you can define a large procedure and call the procedure itself in two different quantum branches with different classical parameters. So this can be done in the recursive fashion. So here we might also have this quantum branch. So that's the intuition. Okay. So last time we are developing a series of quantum programming languages. We start from the simplest quantum circuit, then we add the classical variables, then we define the syntax and semantics for these two quantum programming languages. So the last time we start with quantum circuit, then we go to adding some classical variables, and that's last time we are here, and today we are going to add the procedures. The notion of procedure and procedure calls. So it will become RQC plus with procedural calls. Procedure. and this is with classical variables. And finally, we will arrive at C++. This is with parameterized procedure, or with a procedure that allows parameters. Okay, so let's recall the syntax of the QC class. So syntax QC class. We write it in the BNF form. So each statement can be written as first is the QC, the statement from the quantum circuit. So in quantum circuit, we can perform a elementary unitary gate on a quantum register Q bar, and we can perform a sequential composition of two circuits, and we can do the QF statement. So that's the QC part. Then we add the classical variables. So we will add some syntax that allows you to operate the classical variable. So we have this skip is just mean you do nothing. And you can also perform assignments on this classical variable. So this assignment means you are assigning a list of classical expressions to a list of classical variables. For example, you can write x1, x2, or just x, or x1, y, we assign it to be x1 plus x2, y minus 1, something like this. So this is just a standard classical assignment. And we can also do the classical if then else statement. So if B, then C1, else C2. And here we also have this so-called local block. So that this local block or block statement temporarily assigns some classical variables to some values within this block. So it will be local x bar to t bar, some c, and remember the BNF form says each of these C1, C2, C0, C1 of C here also have this form of C. So this is the structural inductive definition of the syntax. So this is the syntax of QC class. So let's recall some of the semantics for some of the statements. So for example,
just to check,
yeah.
This is some new clauses in the pure QC language.
Yeah.
What's new again? So x bar t equals t bar, that's new?
Yeah, so the statement below these blue lines are about the classical variables.
Okay,
and above the blue line is the original one in quantum circuit. So here you have more control flows about how you can, so the major one is the if statement. Of course you can add some loop, for loop or while loop into this, but here for simplicity I just put the if statement here. And here the Boolean expression B can be computed by these assignments.
Some additional clarifying questions. So
yeah.
The first level QC language, it does not have a terminating skip expansion?
Yeah. Yeah, but you can also add a skip. So skip is just, so in classical they have this skip.
Yeah.
But skip is just mean you just do nothing, yeah.
And then comparing to Tuesday's lecture from Zhicheng,
yeah.
The QC language here does not have an initialization. How do you initialize?
Okay, that's a good question. So the question is, we don't have initialization here. So remember, this whole series of programming language will be describe the unitary transformation. So there is no measurement involved. But if you want to perform some reset or initialization of quantum variables, you need to use the measurement. If you are considering, if we want to initialize arbitrary states and transform it to some zero state, then we need to make some measurements to reset it. Otherwise, if you have a unitary that prepares this one, then you can also reset it.
Okay.
But since our major consideration is about the unitary, so we just assume all of the qubits, not just the qubit, all of the quantum variables, they will be initialized to some state k0. Yeah.
Got it, thanks.
Okay, thanks for this question. And yeah, so now I will still record the semantics from last lecture. So again, this is operational semantics of just the QC plus. So we have some transition rules. So the semantics, remember, it is defined as transition between configurations. So what is a configuration? The configuration space, they are consist of such triples, and each triple has this form C and sigma kit per psi of this form. So here C represents the remaining program or statement to be executed, the remaining program, and sigma represents the current classical state, and this kit per psi represents the current quantum state. So this is the set of configurations. So you can think of configuration as every information you know at some point of the execution. And then the semantics, operational semantics, will be defined as a arrow, which is a relation on this C times C. So that means if you can transit from C sigma kit per psi to some C prime sigma prime per psi prime in one step, that means you execute some part of C and it becomes C prime, and you take the state sigma and kit per psi to sigma prime psi prime. Okay, so that's how you define the semantics, and we will show some transition rules for defining the semantics of this syntax. So the first rule is about the unitary gate. So we can write transition rules U where you apply unitary gate, elementary unitary gate to a list of quantum variables, and you start with some sigma, the psi. Then it will become, after one step of execution, it will terminate sigma, and it will change this state. So it will apply sigma q bar tensor identity on this psi. Okay, so what does this mean? Remember, q bar can be a list of quantum variables. So q bar can be something like q x plus 7 and q prime, say y minus 7, y minus c, 2, or something like this. So q bar is just the list of quantum variables, and each quantum variable also can be a subscriptive variables. So q could be an array, and this means the x plus 7's entry in this array. So when you are referring to a q bar, it depends on the current classical state. Because here, x, y, z, they are classical variables, so they can take different values. For example, x can be 1, y can be 2, z can be 3, maybe not 3, 1. Then this Q bar actually refers to, let's write sigma. So here, this is the sigma state. Sigma is a classical state. So it is assignment of these classical variables to the values. And then we can write the sigma Q bar, which represent what this Q bar refers to. Then it will be Q8, Q prime, 1, 2. So that's the actual quantum variables Q bar represent under the classical state. So that's why here we have sigma Q bar. So you need to apply this unitary on sigma Q bar. Of course, remember last time we also need to promise that this unitary does not, Q bar should be a list of distinct quantum variables. So we need to add some condition here. So this condition is sigma satisfy these Q bar are distinct. For example, we are not allowed to perform such, to execute such statement like Q1, Q1, because you are applying C0 on the same qubits. For example, Q1, Q1 are the same qubit. So we should prohibit such behavior. So we need the current classical state to satisfy this a Boolean formula state saying the quantum variables in the list of Q bar should be distinct. And here I will not explicitly write out this formula. You can just write it out using the first order logic. Okay. Then what's the most important part is the semantics for this QF statement. So for QF statement, let's write the QF rule. Here is just a formal definition of our previous intuition of what is a quantum control flows. So assuming we start as a state kit per psi, and it can be written in this form. So you just expand this state in the basis of the controlling qubit or quantum coin. So you expand it into this basis of, and psi. And you assume each Ci will take sigma theta I as Ci terminate sigma prime theta I prime I0 and 1. And this QF statement will take this one to be termination sigma prime and alpha 0, 0, theta 0 alpha 1, 1, sigma QL, theta 1 prime. Okay. So here, this vertical line, this horizontal line represents when you have these premises, you can have this conclusion. So what does this mean? When you expand the initial state into the basis of these controlling qubits, and each of these quantum branch Ci takes sigma, the same classical state sigma, and quantum state theta I to termination, and you end two branch end in the same classical state sigma prime, and it could be something different quantum state theta I prime. Then you can write the execution of QE statement and it will transit to these configurations. So yeah, so this QIF, just you can intuitively, as we previously shown, you just apply the semantics of CI on this on theta 0 and theta 1 in superposition. But remember, here we have some condition here. So in this two quantum branch, I equals to 0 and 1, they take the same classical state sigma to the same classical state sigma prime. But the quantum state can be different. It can be theta I to theta I prime. So why we restrict the classical to be, why we restrict these two quantum branch? So they start with sigma and same sigma and theta 0, theta 1. Why we restrict them to take them to the same sigma prime, but can allow them to have different theta I prime? The reason is, so this is a condition. This condition is to disentangle classical and quantum. Because we need to keep the classical variables to be always classical. So if you allow this sigma prime to be different, for example, if we allow it to have sigma 0 prime and sigma 1 prime, then these classical variables are no longer classical variables, because it will be entangled with this theta I and theta 1 prime. So once you allow this classical two quantum branch to terminate in different classical state, then these classical variables are no longer classical. It will become quantum. And that's not what we want, because we want to always separate classical and quantum variables. So we need to keep these classical variables and quantum variables disentangled. So that's why we have this condition here. So last time, one of the audience asked whether this will put some restrictions on how we can write this qubit statement. And to address this problem, we need to have using these local block statement. So this block statement can help programmer to write program that satisfy this condition. So how can we use this local statement? So here is the rule for the local statement, for the block statement. Just write it here. So for the block statement, the transition will be begin and sigma keep aside. It will become x to t prime, and you execute the C, and you reset the original value of x bar. Okay. So here we have these reset. So the block statement means you temporarily set the values of x bar to the values of this list of expression t bar within this block. And once you arrive at the end, you will set the values of x to its original values. So that means x bar is just the local variable within this block. So when we interpret this into formal semantics, that just means when you execute this block statement, after executing x bar assigned to be the value of t bar, then C, at the end you will assign the original value to the x bar. So this is just defining the semantics for this block statement. Okay, so
sorry, I don't quite follow. So the right side semantics there, that's a 4 tuple? There, yeah, like the.
It's a triple. It's still triple. So this part. So this part is the. I mean the remaining statement to be executed.
Okay.
And this is a classical and this is quantum state. So that means after one step of transition, you have this statement to be executed.
Yeah, okay. I was just parsing that list wrong.
Yeah, okay.
The semicolons have higher precedence usually than commas.
Okay,
Yeah.
thanks for this question. And so this basically says the locals, the local variables are local within this block. It's just like the standard classical local variables. For example, when you write some C++ program, you have some local variables, and these local variables, they are only alive within the scope of this local block. But here, we are not like, our program don't have a declaration. We don't define all the variables at the beginning of our program. So we implicitly define. When you use it, you define it. So this part just, you temporarily set this x bar to be local variables. Okay. So using this local statement, we can kind of use this statement to construct some QF statement. I mean, we can use this to write program that satisfy this condition, because what's good about this local statement is before and after you execute this local statement, the value of the x bar is not changed. And that's what we want. This one is actually stronger. So that means if we set all classical variables to be local, then if it of course satisfies this condition, because here sigma prime is just the sigma. And of course you can also manually set some classical variables to be to the same classical variables. A local block statement can help you to satisfy this condition. Okay, so that's what we talked about in the last two lectures. Is there any questions so far?
Yeah, one question. So the GA semantics allows for unitaries of any size, right? Because Q bar can be a list of qubits.
Yeah, so here Q will be select from a set of elementary unitary gates.
So, and then technically QIF is completely within GA, because QIF is just specifying a special kind of unitary, which is controlled unitary.
Yeah, you can think of it in this way, but so the question is asking the QF statement can be like
Subsumed,
yeah, you can express it as a large unitary, but since we are considering a program, so we are restricting what kind of U you can use. So for example, we can choose so that's the alphabet for what you can choose. So before defining this programming languages, we will fix the set of elementary unitary gates. For example, we can fix it to be the whatever a universal gate set like H, T, C naught. We can also add this Pauli, and you can also add rotations. Depending, so the language is here. We are just talking about the theory of theoretical construction of this language, but depending on what, in practice, depending on what elementary unitary gates are provided, we can like fix this set of elementary unitary gates. Yeah, so this is just, so these statements are like building block of this language. So once we set the elementary unitary gate, and we can use these building blocks to construct a larger programs that describe a more complicated unitaries. Does this answer your question?
Yeah.
One question.
Yeah.
So, I think you said like Q if we need to keep the elementary be the same, because eventually when every program goes to the last.
Yeah.
And so in this way we can use like local variables to do it in the first and do it in and convert it back after the local block being executed. So why this restriction have been done in the last step? Why it's not being like in the next step, but it's been, so why this restriction should be right after the last step in the terminating step?
Okay, so are you asking why when we create two quantum branch and we are assuming like the last step they have the same classical state, not in the middle?
Yes.
Okay, good question. So here this semantics is a large step semantics. So here we are, so here one step of this QIF execution, it just finished the whole execution of this two quantum branch. So if you have, so I should answer it in this way, because the last step is what we concern. The last step is when we finish this two quantum branch, and then we will meet this end of this QIF statement, and these two quantum branch will be merged into one. So this QIF is first to create two quantum branch. Then this two quantum branch, it is guarded by this controlling qubit, and after executing this two quantum branch, these two branches actually merges. So during the execution, there is sigma. So for example, yeah, during the execution, their sigma can be different. They don't have to be the same. I will show you by an example. So for example, we have one program, one procedure called P. Let's just write it this way. It's x to be x plus 1, and then we apply some u on qx. Then we set back. So here we are not using the local variables. I just want to illustrate the process. So we manually set back, set x to be its original value. Then we have another procedure, but it goes through different ways of computing x. So for example, x can be x plus 3. Then you maybe do one more, for example, x plus 1. Then you perform another unitary v on qx. Okay, and here we just set it back to before. So these two procedures, before and after executing this procedure body, the value of x will remain unchanged. So they can be used in this QIF statement. So for example, we have another procedure PR, says q prime is a qubit, and you execute 0 to P and 1 to Q. And this is a valid procedure call coding P and Q in this Q statement, because before and after executing whatever x is, whatever the initial value of x is, the value before and when you finish this branch, the value of the x will remain unchanged. And this one is the same. But they are going through different route of computation. So when you execute this quantum branch, the first quantum branch, it will first add x equals to x plus 1. Then you do something, then you x equals to x minus 1. And the second quantum branch will first do x equals to x plus 3, then x plus 1, then do something, then x minus 4. So during the execution, they go through different routes, although they are terminating in the same classical state. So we cannot make every classical variable. I mean, we cannot make the classical state to be always the same in two different branches. Does this answer your question?
Yeah.
Okay, great. Great. Any more questions? Okay, great. So now we can add the procedures, the notion of procedures. And once you have the procedure or recursive procedure calls, we are done. Once you have that, we can do the quantum recursion. So I will keep here and just remove this one. So what we are going to add is, we first, in our alphabet, we will add a set of procedure identifiers. So you can roughly think of it as, as the name of procedures, identifiers. And we will use symbol like P, P1, P2 to represent procedure identifiers. For example, when you write some QFT and you define this procedure, and this part is a procedure identifiers. And now we are not considering, so now we are going to define this RQC+, and we are not considering the classical parameters yet. So we have these procedure identifiers, and we will add into our syntax a statement called procedure call. So it is just a P. P is some procedure in these procedure identifiers. So what does this mean? Then we also need the notion of called procedure declarations. So procedure declaration is a set P that consists of these, for example, Pi, you define it to be some Ci. So each of these declaration has the procedure identifier on the left and a statement or program on the right. So here Ci following the form of these statements. So that means, so the right-hand side is called procedure body. Procedure body. And this is procedure identifier. Okay, that's the procedure declaration. And now we can explain what is the procedure call. So when C is P, that means you call the procedure under the procedure identifier P. So we can write out the semantics for, so now here this should be RQC++. So the semantics for the procedure call is the so-called copy rule. The copy rule says, okay, so if you have P defined to be some C, and in the procedure declaration, then P sigma kit per psi, you just copy the procedure body. So that's very natural intuition for the procedure calls. When you call this P, you just put its procedure body to execute. So this is the procedure declaration and procedure call without classical parameters. Yeah, and now, is there a question about this part? Okay. And adding the classical parameters is actually simple. So when we move from RQC plus to RQC++, we just add the classical parameters. for the procedure call. So now the procedure identifier remains unchanged, but in the declaration, we can allow this procedure identifier to have some classical variables as its parameters. So these parameters are called formal parameters. This is called formal parameters. And this is kind of standard in classical programming languages when you write some, for example, when you write some C++ program, you write like sorting algorithms, then you might include, for example, sort, and then you define this sorting algorithm, right? So this n is the formal parameter. And once you have these formal parameters, you can call the procedure P with some actual parameters. So here T bar is a list of classical expression. This is called actual parameters. Actual parameters. Okay. So what does such kind of procedure call means? Now we don't have this copy rule. What we have is this RC. RC means when you have P, P U bar defined by C in this set of declaration, then this procedure called PT bar becomes, we will use the block statement to define the semantics. So it will temporarily assign the formal parameters by the value of the actual parameters. So you can write again local U bar to be T bar. Then run the C and end sigma assign. So that's the semantics for procedure call. So what does this mean? When you execute a procedure call with actual parameter T bar, you just temporarily replace all of the formal parameters U bar by the actual parameters. Then you copy the procedure body here to run it. So that's the procedure call. So where can we use recursion? So in CI is any statement satisfying this format. In CI, we can also, for example, we can just let CI to be PI. Let's make it more explicit. For example, we can just write PN to be, this one is CI, this one is C. So here we can just write PN minus 1. Because C only needs to satisfy this syntax. So C can contain some P T bar. So this is U bar, this is T bar, and this one will be in the procedure declaration P. So that's the, here we can see how we can call a procedure itself recursively. Is there any questions so far?
One quick question. So it's like after the ends, like the U bar in the environment just vanishes, right?
Sorry, you are referring to this one?
Yes.
Yeah, so the question is?
So like we have begin local and we assign U bar to some T bar. And
yeah.
We see after the ends, like the U bar just vanishes.
Yeah, U bar, you can think of it as vanishes. So U bar will be no longer available as the formal parameters of P. But maybe some other program might also use the same name, U bar.
Oh.
Right, so that means just within the scope of this block, you are regarding U bar as the formal parameters of this procedure. But outside it, other programs can also use U, right? You only have that many symbols, so you need to repeat to use them. Okay,
Question.
sure.
So in the definition of RC, the extension there,
Yeah.
it is guarded by the requirement that C
Yeah.
has to be a member of procedure declaration. C belongs to P.
Yeah, sorry. Here there's some slightly ambiguity, so we are actually saying this whole thing is in the procedure declaration. So each element of the procedure declaration has this form. On the left-hand side is the procedure identifier, on the right-hand side is the procedure body.
Do we declare all possible? Never mind. I don't think this is important.
Oh, okay. I will explain more. So when you write a program, you will define a set of procedures.
Yeah.
For example, when we write some QFT program, we might define some other procedure that can be used in the QFT. For example, you can define a shift, you can define a rotation, and all these are procedure declarations. So each procedure declaration, you also need to define what does this procedure mean. And when you collect all these procedures into a set, this is P. And P, you can roughly think this is the actual program you are writing, because you are writing a set of procedures. And among this P, that's more tedious detail, you might have a main procedure. That when you write classical program, you often have a main procedure or main function, right? You might, for example, in the C++, you have the main. And the main procedure will call these other procedure or functions. Here we are not considering functions because we just described the unit tree. So you can call these procedures. Yeah, and this P is the program you write, actually. Okay, but I will show you examples after this part. So here we already finished the syntax and semantics for recursive, for the quantum recursive programming languages, RQC++. And now I will show you through a series of examples and take a look how we can use it. Okay, so now let's start with the examples. I will keep the syntax here, but erase the semantics maybe. So I'll just do it in this part. Okay, so here I should also put the procedure declaration here. So when you write a program, you have this procedure declaration. So I just put it here. P, for example, P1, U1, C, something like this. That's just a collection of procedure declarations. So now we start from our example part. So first, the example will be, so let's first start with an example without quantum control flows. And it just contains the procedure calls, but it is still a quantum program. But the recursion in this quantum program is essentially classical. So here, so now next we can see the difference between classical recursion and quantum recursion. So this example is the GHZ state. The generation of GHZ state. I will write the full name for it. So it's a Greenberger-Horn-Zellinger state. State generation. So this is an example of classical recursion. So the GHZ state, we can define it by this way. So we have some parameters because it can has so this should be call the generalized GHZ state. And it is defined to be square root of 2, 1, 0 to 1, 1. Yeah, so this is the generalized GH state, and the GHZ 1, 3 is the normal GHZ state we are more familiar with. So this is 0, 0, 0 plus 1, 1, 1. So that's the original GHZ state. You just take the parameters to be 1 and 3. Okay, so how to generate this GHZ state? We can use a classical recursion. And of course, our language can also express classical recursion without using the QF statement, because we allow, so you can define the procedure. So this is the P you are defining, GHZ, Mn. You define it to be if m equals to n, then you do a Hadamard gate on Q. Else, you just call this procedure recursively. U n minus 1. Oh, sorry, n C not. That's a program, and this is the whole P, where here we have we define a procedure UGHD MN, and if you apply this GHD MN on some initial state, on some zero state. So here we implicitly assume all quantum variables are initialized to 0, and when you apply the corresponding unitary to this K0, you will obtain the GHD state. So how does it work? When m is equal to n, then here it is just the state plus state. So this is when m is equal to n. You just apply the Hadamard gate on Qn, then you will have this state. Now, what if m is smaller than n? Then we can recursively call the procedure UGHD n minus 1. So that means if you have such state, for example, n minus m, you take n minus 1, so it's n minus m plus 1 plus n minus m. So this state can be generated by this procedure call, and it is a recursive procedure call with different classical parameters. Then you further apply the C0 with this. So this one is Qn, and this one, they are state of the quantum array m to n minus 1. So at this point of the program, we have this state where this part are generated by this recursive procedure call. So we can further apply a C0 between Qn minus 1 and Qn to further add this qubit into there. So after you apply the C0, it will become a state on Qmn. You have this 0, you have this 1, and this is a GHD state of Mn. So here you can see how you can define a quantum algorithms using classical recursion.
What if I call GHZ 2, comma 1?
GHZ 2, 1. Oh, you are saying m is larger than n. Yeah. Oh, okay, that's a good question. So in this case, there should be some error. So here, maybe we need to add some additional condition to promise that m is always less than n. But it's not I mean, you can enforce that, for example, you can write a main program, main, and if m is, for example,
Okay, yeah, I get it.
yeah, you can understand that. You can just enforce this m is always smaller than n.
Then another question, just nitpicking, why do we use C0 unitary here instead of using the QF?
Okay, great question. So the question is why we are using C0 here instead of using QF. Okay, this is just for demonstration. Of course, C0 is equivalent to this QF statement. Yeah, so they are equivalent. But I mean, once you have C0, you don't have to use. I mean, C0 is just the QF on. You can write it in this way, of course. Actually, here it's better to use skip.
Would one be preferable than the other in this case? Are they equally easy to verify?
I think in this case there is no difference. So it's just a matter of how you want to write the C0.
Okay.
Yeah. Yeah, of course you can write a lot of like different forms of program to describe the same algorithm. Yeah.
One quick question. So,
Sure.
So first, why GC have 2 variables? Seems like just we can use
Oh.
variables too.
That's a good question. So why we are using m and n instead of just using n? Yeah, so that's it's just a matter of I mean it is possible you can write it using just the one variable. So it's just for illustration. Yeah, and in the following we will see other using just the one variable. Yeah.
Okay.
You're right. You're right. Here it can be simplified to one variable if you're using some trick.
Okay.
Okay, great.
Another question
Sure.
is so this program, it has a lot of like if branches.
Yeah.
So in this case, in what case can we verify, for example, it's following that after the if converges,
Yeah.
the traditional variables are like they converge, it does not entangle.
Okay, great question. So the question is about how we can promise the semantics, the conditions that 2 quantum branches terminate in the same classical state
Yeah.
for the QF rule for the semantics. Okay, that's a great question. And here we are not like bother considering how to check the grammar and semantics of the program. So, but we, as we previously mentioned, we can use the local statement or local blocks, the block statement to satisfy that condition. So this is up to the program part. I mean, this is the duty of the programmer to promise that the program is always written correctly. And of course, in the next step, maybe in the future work, we can also develop some tools to check whether a written program following satisfy the correct syntax and semantics. But yeah, great.
And I believe this is true, but there is no way to write UGHZ, this program, in any language less than RQC++. It's not possible to write in RQC.
Actually, that's a great question. So this is about the expressibility of the RQC++. And for this program, actually you can do it in other programming languages. For example, in one paper by the teams in Maryland, sorry, I forgot about their initials. So I should check. TP.hill. In this paper, from the teams of University of Maryland, they defined a language called. So this language, they allows a description of classical recursion. And since here, the GHG states of this program, here we only use the recursive procedure call, and we haven't used the QF statement. So this is essentially a classical recursion, and actually in their paper they also use the GHD as an example of their language. So, and one further comment is recursion. Of course, I mean every valid quantum programming languages, they are already Turing complete. So recursion does not increase the computability or something. So that means we cannot say we can write some quantum recursive program that cannot be written in other language. After all, you can write it, but that could be more complicated, and that could you might write a long program in another language to describe the same algorithms. But here, once you use the recursive structure in this algorithm, then we might write it in a more elegant and more compact way. So that's the reason why we consider the recursion, as in the classical case. This is similar. It provides you more convenience. Yeah. Does this answer your questions?
Yeah.
Okay, great. Thanks for this question. Yeah, so that's about the motivation of recursion, and in lecture 1 we slightly mentioned this, and in the following 3 examples you will see, you will feel more about this when you can see some more complicated examples. Okay, so this is just a classical recursion, and now we will show an example of quantum recursion. This is quite a simple example, but it will give you some flavor of what is quantum recursion. So just a very simple construction called multi-control gate. Multi-control gate. So this multi-control gate, if you write it in the circuit quantum circuit language, it is just this. You have multiple controlling qubits, and it's one. So this is often written as some CNX, not X.
U.
Here U. Yeah, you're right. U. And it just means once you have all these. I will write it in this way. So when you apply it to some I, write it in this way, I M to N and some, yeah, and minus 1 maybe. Minus 1 psi. It will become, you apply this U only when all of the controlling qubits are in state kit 1. So it will become this one. You apply this U if, for example, for OK smaller than minus 1 IK is equal to 1, and otherwise you do not make any changes to psi. Otherwise, yeah. So that's the how you describe the multi-control gate mathematically. You can do it in this way. It just says when all of the controlling qubits are in state kit 1, you apply the unitary. Otherwise, you do nothing. And of course, here this state we just define it in the one basis of the Hilbert space, and you can expand it into a superposition state. So for example, here you can be something like alpha I, and it can be just alpha I, and I can be different, right? The psi I. It can be in superposition state. So how can we write it in using our RQC++? And here we will use the notion, we will see how we can use the quantum recursion. Okay, so we write a program called C star U, where star represents, here the number of controlling qubits can be any a parameters, and n is if m is equal to n, then you just apply u to qn, and else you need to q if, you need to check this q, I think it's q m. If it is 0, then you do just skip, and if it is 1, you call the CU itself. C star U itself, C star U itself, but with m plus 1 n. So that's a program. And where here we use this QF statement, and in the quantum branch, we call the procedure itself. So this is a simplest example of quantum recursion. You can see the interplay between the quantum control flows and recursive procedure calls. So that roughly means when you have m is equal to n, then there's no control. So you just apply a u on the qn. Otherwise, so you have these q, m, n minus 1. And so the first several qubits are for the control. And the last qubit is being controlled. So what the program does is if there's no control qubit, you just apply a u on the last qubit. Otherwise, you check. So this is where you add m. You check n. Actually, here we have something there. You check this m, qm. If qm is in some state k0, then we just do nothing. We can if there's 0, then that means we belong to the second case. So we just do nothing. Otherwise, we continue to check the next controlling qubit. So when it's in state kit 1, then we will call the procedure with n being n plus 1. So we move to this n plus 1. So that's the idea. Is there any questions?
Yeah, I have a very difficult question.
Yep.
And probably it's too early to ask this, but so we can, this program includes the total gate, which is control not, control X.
Yeah, yeah.
The Toffoli gate has a typical decomposition into single qubit T gates and a CNOT gate.
Yeah.
That circuit looks nothing like this semantics here, but they are equivalent, right? They are actually functionally the same.
Yeah.
How might we be able to show that they are equivalent, that they evaluate the same thing?
Okay, that's a good question. So the question is asking, okay, so this multi-control gate will include the Toffoli gate, and there are other ways to decompose the Toffoli gate into 1 and 2 qubit gates.
Right.
So how can we verify these two expressions are equivalent? Okay, so so I should say currently we don't have a way to verify whether quantum recursive programs its semantics is equivalent to some other unitaries, because here the semantics. I need to first mention one of our works that's about the verification of quantum recursive program. So this work consider the verification of program within this syntax. So that means if you have two programs in this RQC++ syntax, you can verify whether they are equivalent using the proof rules. But the question you are asking is whether we can verify this program with another expression using quantum circuit. So it becomes at a lower level, because this program, when you're expressing its semantics, you are actually describing the unitary, right? So at that level, you are actually verifying whether unitary is equivalent to another unitary expressed by a circuit. And this becomes the problem of like verification of quantum circuit. And yeah, and it is like first beyond the scope of our discussion here, and this is of course a very interesting and important question. And there are a lot of works about the verification of quantum circuit and verification of the equivalent. Actually, it should be called equivalence checking between two circuits. And of course, you might have different expressions. You might have also different equivalence checking systems. Yeah, and that's a very complicated topic. Yeah, so the answer is no. We currently don't have a way to verify that. Of course, you can convert it to a unitary, or we also do the compilation of this program to compile it into a circuit. So you can also do it in the circuit level, but that could be very complicated. Okay.
One quick question. So,
Sure.
I wonder, like, does you have like a notion of complexity in quantum? It's like, so this gate you sees looks like just goes one path, but your algorithm or your programming language looks like it's going to a linearly, like checking state by state. This
Yeah.
So how do you explain this?
Yeah, that's a good question. So the question is about how to compare the complexity of different ways to implement or express the same unitary, right? So in quantum, typically the standard complexity measure is in terms of the low-level quantum circuit. So if you have a quantum circuit, first, this is a unitary. You need to decompose this unitary into the elementary 1 and 2 qubit gates, for example. You can decompose it into, as Yipeng has mentioned, you can decompose it into hopefully into 1 and 2 qubit gates. And of course, you can also decompose this multi-control. And actually, this multi-control, you can decompose it into a quantum circuit with 1 and 2 qubit gates. In probably, I think it's ON, CU, and no, not this one. First, C and X, I think it can be decomposed into a quantum circuit of ON, 1 and 2 qubit gates. And you can use C and X to construct this. So using one ON elementary qubit gates with an additional controlled U. So you only need this one. So that's the standard circuit decomposition of this unitary. And it's pretty good. And what about when you have a program? So the program here, we are still considering how to describe this unitary. We haven't yet mentioned its implementation. Of course, when you, in the next 2 lectures, I will talk about implementation. And in that step, we can analyze its complexity. But the complexity, when you also compare it in terms of the standard circuit complexity, it will depend on the quality of this program. So when you have different ways to program the same unitary, they might have different complexity. And using this way, as you have observed, its complexity should be like, because you need to check each of the control qubits sequentially, so the depth of this procedure will depend, scaling roughly like ON. But if you use the optimal decomposition of this multi-control gate, the depth can be better than you describe it as a program. Yeah, so writing a program cannot always promise you have the optimal implementation of an algorithm. But the programming language is more from a universal way to describe algorithms, and of course we hope to achieve as optimal as possible. And in the next two lectures, when I talk about the implementation, we will see in many examples actually using the quantum recursive program to describe the algorithm is efficient in terms of depth complexity. Yeah, so there are like two factors that affect your efficiency. The first is how you write this program, and the second is how the machine compiles this program into circuit. So remember, the programming language is a bridge between the human and the machine, the computer. So this part, you write the program, and the quality of how you write this program will affect your complexity. And this part is the compilation and implementation part. That part will also affect your complexity. And programming languages, one goal of programming languages for the convenience of the human. So convenience is also an important factor. So programming languages does not always offer the best efficiency. Yeah. So that's roughly, yeah.
Okay, thank you very much.
One additional question.
Sure.
I think I just want to double check with what what you say just now, because we know like multi control U gate or multi control X gate has different implementation.
Yeah.
Like sometimes they use like a ON as zeta qubit, and sometimes they use 1 as zeta qubit, and sometimes even I think some implementation they use 0 as zeta qubits.
Yeah.
But I think that will be something you call like a compiling step, like between compiling programming language and the machine.
Yeah.
It will not related to the program syntax you write down in the first step, right?
Yeah, you're right. So the question is, currently many proposal for the quantum compilation is about how you can compile such unitary into elementary quantum gates, right?
Yeah.
So that means they are considering a more low-level programming language. For example, you might have some circuit-level language that has such syntax, and then you compile it into some
Assembly code.
elementary quantum gates. So yeah, that's a good way to think about it. And so when you have, so here the recursive programming languages is more about, it's more a high level programming languages. So we have a high level, and here in the compilation you might have multiple levels here. So in each of these compilation paths, you might optimize, right? But this procedure, of course, cannot beat in efficiency that you directly optimize using the most optimal circuit description. So that's the price you need to pay for the convenience. You split the description into multiple levels, and you optimize it in each step, and that, in terms of efficiency, cannot be better than you just optimize the whole steps. But once you have multiple levels, first it provides more convenience. Second, you have different opportunities, different optimization opportunities in each of these steps. And that allows you to construct a very large and more complicated program. Because if you want to describe a program, for example, it is a program about like a million qubits, then
Infeasible.
it is infeasible to optimize using the low-level optimization. So, if you have some high-level construction, you can first describe it in high level, then to mid-level, then to low level. So you have multiple levels, and that becomes more easy to handle. So this is just like the classical programming. In classical, we program and do not write in machine code, right? But machine code is most efficient. If you can just write the machine code, then it's the most efficient way. Okay, I think there's not too much time, but I would like to mention one more example to show you. So just one more example, maybe 5 minutes. And next time I will cover 2 more examples, but this time I will mention one more example. This example is, I think it can demonstrate why we consider quantum recursion. So there is called so-called decay state generation. So there are some quantum states that are intrinsically recursively defined. So one example is this so-called decay state. So it is defined like this. D and L is defined as Ln D n minus 1, L minus 1, 0. Sorry, I should not write it this way. I should write it this way. N minus 1, L minus 1, 0 plus square root of n minus L n D n minus 1 L 1. Sorry. Here should be 1. Here is 0. So this decay state is, it is intrinsically recursively defined. So how can you write it? How can you write a program or design some quantum circuit that generates this decay state? Okay, so the intuition is if it is recursively defined, then we should use a quantum recursive program to describe it. So, for example, UD, we can write UL if n is 0 or L is 0, then you skip, else you perform a rotation on this Qn and Q if it's 0, then you call the procedure Dn and minus 1 L. If it is 1, then you call the procedure minus 1 L minus 1. Alright, so this is a quantum recursive program in RQC++ to describe a procedure for generating the decay state. And as you can see, it naturally follows from the definition of the decay state. So if you n equals to n, L equals to n, that's a boundary case you just skip. Otherwise, you first rotate the last qubit to introduce the amplitude, the square root of this part here. So this part is just you introduce this amplitude by rotating the last qubit. And then you use a QF statement to condition on the last qubit. Then you call the procedure itself to generate the decay state with different parameters. That's very natural to define it, to define the program that generates this decay state. And and it seems not very easy to directly design a quantum circuit for generating this state, right? Because it is naturally recursion. And once you have these tools with quantum control flows, and this recursive procedure calls, you can do it. Okay, I think that should be the end of today's lecture. Is there any further questions or comments?
I guess just a definitions question. So
Yeah.
2 days ago, Min Shen's lecture, he explained that there's different types of semantics, denotational, axiomatic.
Yeah.
What are the different levels again?
It's starting from the most low level operational semantics, then denotational semantics, then axiomatic semantics.
Where are we operating here?
We are doing, what we introduced previously is about the operational semantics. So it's more concerned about how you describe how a machine executes this program. And when you, so if you want to study like the mathematical structures or properties of the program, you will need to go a high level up to the denotational semantics.
Will this go to denotational?
No,
This one does not.
Yeah, so we will just remain at the operational semantics. Because I mean, of course you can define denotational semantics and more high level, but that's, I mean, it's like when you want to study the mathematical structures of the program. And since this one is like the initial steps into these directions, we are still considering like the low, so that like the operational semantics part. And this will also help us to how you design the compiler. So when you design compiler, you need to regard the semantics. You want the compiler follows the semantics.
So for example, the GHZ state.
Yeah.
The program that you wrote on the GHZ,
yeah,
it shows that you get the state vector. You get the kind of state vector implementation.
Yeah, so GHZ is, you are actually getting a
circuit, right? Yeah.
Yeah, and when you apply to initial state 0, you will have this GHZ.
So this is operational semantics. Now
Yeah.
the denotational semantics of GHZ, I don't know if it's denotational semantics, but in natural language, what the GHZ state is we should claim that it has bipartite entanglement.
Yeah.
Right? It's just the state that's entangled,
Yeah.
and it's however many copies of the qubit.
Yeah.
That level of meaning is denotational semantics? Or
Yeah.
it
So
doesn't belong in this.
yeah, good question. So the question is does the mathematical language about the GH state belongs to the denotational semantics? And I think from my personal view, this denotational semantics might provide you a way to study properties at that level. So actually we can directly define the denotational semantics using the operational semantics. So the denotational semantics, for example, you have a program, P, then when we consider its denotational semantics, we often use this double bracket. It will be, you actually consider this as a operation. For example, in our case, this is just the unitary, so it is a mapping, a unitary mapping from Hilbert space to Hilbert space. So you are actually studying this as a unitary transformation. So at this level, of course, you can study something like, for example, you can study something like P when you apply to 0, and you have this GHZ, then you can study like the entanglement entropy or something about this, and this is more at the mathematical level.
Mm-hmm.
Yeah. But I think using denotational semantics does not provide, I mean, it is not a way you can have study more properties about the state, but instead, since program, what we mostly handles are like the control flows or something. For example, if you have a while loop, you might need to study the properties of this while loop, whether it terminates, or how long does it terminate, or the probability in quantum, the probability of the termination. So that's more about programming properties we want to study.
Mm-hmm.
using this denotational semantics. But the property you mentioned about the entanglement is more about, I don't think it could be a program property, it could be some property just by the, I don't know, maybe just the property of the unitary transformation. Yeah, thanks. Great. Is there any questions? More questions? No? Okay, great. Thanks everyone again for attending today. And in the next 2 lectures, I'll give you further more examples, including the quantum Fourier transform and how to write the QRAM, quantum random access memory, using this quantum recursive program. And then I will describe its implementation, including the compilation, partial evaluation, and execution. And we will design a new architecture called quantum register machine that supports the quantum recursion. Okay, thank you.
Thank you.